Great. Yeah, we can see all that. And we can see that if you can put on the full screen.
Yeah, how's that?
Perfect. Yeah.
Okay.
Well, our last speaker of this session is from Professor Douglas Strout from Alabama State University. Topic is on the screen: effective oxygen insertion on the ring strings, isomer stability of N12 cages. Floor is yours.
All right, great. Thank you. Thank you. I get to pitch the ninth inning here. I get to close the whole deal out. Well, I'm Doug Strout of the Department of Physical and Forensic Sciences here at Alabama State University. I know that name change for our department is not official yet, but it's my title slide. Yeah, we're going to be talking about cage molecules of nitrogen with 12 atoms. And let's get to it. Let's get into it. High energy nitrogen is the motivation here. That large nitrogen molecules, large systems of nitrogen, they're highly energetic, and they're of interest research-wise for that reason, because any molecule with X number of nitrogen atoms can decompose all the way down to N2, which is just, it's almost 80% of the atmosphere we're all breathing anyway. That's a very stable molecule. Those are very exothermic reactions. They release large amounts of energy, and that's why folks are interested in them, because they're energetic. Now, if you want a high energy system that's actually good for practical applications, stability is an important issue. Simple example, the gasoline in our cars waits for us to turn the key, right? And we'd be in a lot of trouble if it didn't. It's an energetic, the compounds we use in our cars are highly energetic, but they wait to be ignited because they are stable enough and only respond to an ignition signal from us. You don't want your high energy molecules just spontaneously decomposing out of control. One molecular feature that works against stability, though, is something called ring strain. Ring strain is a concept, we talked about that in organic chemistry and so forth. It's a molecular structural feature that works against stability. Let's talk about that for just a moment. We're going to be looking at cages of nitrogen. Each nitrogen atom will have 3 single bonds, be very much like ammonia. The H-NH angles in ammonia are about 105 degrees, and nitrogen is very satisfied that way, thermodynamically. If we compare that to the basic geometry of polygons, triangles have angles of 60 degrees, obviously squares 90, pentagons 108, very close to nitrogen's ideal. So you'd expect a pentagon-rich environment, to be very stabilizing to a complex nitrogen system. If you force atoms away from their preferred bond angles, well, there's an energetic price to be paid for that in the stability of the molecule. So let's get to the systems. We're looking at these 3 cages. I've named them just very simply according to the polygons that make up their networks. So isomer 3,5 has triangles and pentagons. Isomer 4,5 squares and pentagons. Isomer 4,6 is squares and hexagons. There are a lot more N12 cages than this that have been studied, but for simplicity, I chose these 3 as a representative sample of the polygons. The work that we do in my lab is computational in nature. Did I synthesize any of these molecules in my lab? No, that's not the nature of our work. We're studying these molecules in computational models using what is known as density functional theory. We're using the Dunning polarized valence double zeta atomic orbitals basis set, and I'm using the Gaussian 16 computational software. Gaussian Incorporated, I don't know why I threw their logo onto this slide, maybe just to color it up a bit. I'm not one of their spokesmen, but I do make extensive use of their software in my research. So this is the method, this is the how of what's going on in this study. This is how we do what we do. So let's take a look at some results at the first level. What are the relative energies? What is the relative stability? I'm going to be showing tables of this kind throughout the presentation. And the most important thing to know is that lower energy means greater stability. The lowest energy molecule is of greater stability. So the N12s that I showed you before, the most stable one of the bunch is isomer 3,5 with the triangles and pentagons. And as you can see, it's not close. Isomer 4,5 is less stable by a couple of hundred kilojoules, and isomer 4,6 more than 600 kilojoules. Now you might say, why? Didn't I just get done talking about ring strain? And don't triangles have the most severe restrictive angles regarding the nitrogen atoms, those 60-degree angles in the triangles? Why aren't they penalizing? Why aren't they penalizing the structure severely? Well, to some extent they are, but to keep in mind what's going on in isomer 3,5, does it have triangles with 60-degree angles? Yes, but it only has 2 of them. There are only 2 triangles in the entire structure. The rest of the structure is made up of these very ideal pentagons, which are greatly stabilizing as far as the molecule is concerned. Isomer 4,5 has 4 squares in it. Isomer 4,6 has 6 squares in it. So in the aggregate, you put enough squares in the structure and it will penalize even relative triangles. So here's our question though. Given this starting place, question. Let's bring up our question here. Oh, there we go. No. Question. What if we relieved the ring strain? What would be the effect of relieving the ring strain by the insertion of oxygen atoms into the strained portions of the structures? How would that affect relative stability? How would that affect the outcomes? So let's insert one oxygen atom. My nitrogen atoms are yellow, my oxygen atoms are red. Let's insert one oxygen atom into the triangles or the squares of each of these compounds. I mean, each of these molecules, excuse me. And how do these structures compare to each other relative to the N12s that don't have any oxygenation? And let's take a look at that. I've got N12 and N12O side by side here, and even one oxygen insertion has a dramatic effect. Notice that with a single oxygen atom inserted into the structure, isomer 3,5 is no longer even the global minimum. Relieving the strain of 2 of the squares in isomer 4,5 has stabilized that molecule so dramatically that it now, you see the negative number, negative 15.7 kilojoules. That means that that molecule, which was 200 kilojoules less stable than isomer 3,5, with even one oxygen insertion, is now slightly more stable by 15.7 kilojoules. Because relieving 2 of the squares is a greater effect than relieving one of the triangles. And just as an O, by the way, if I insert an oxygen atom into a triangle, that triangle is still now a 4-membered ring, isn't it? So there is still ring strain in the 4-membered ring of N12O, even though it's been oxygenated. A 3-membered ring becomes a 4-membered ring. It's still strained. So let's continue the process and see what happens. Let's oxygenate all of the structures a second time, doing it in such a way as to maximize the relief of ring strain in all cases. I would especially direct your attention to the middle structure, isomer 4,5, which has been oxygenated twice now, and notice all 4 of the squares are gone. That molecule now consists of nothing but pentagons, which should be a very stable structure. Let's go to the numbers. And there you have it. There you have it. Another 200 and some kilojoule effect has taken place upon oxygenation the second time. And in fact, you can see even isomer 4,6 has now moved within 100 kilojoules of isomer 3,5. But isomer 4,5, oxygenated twice, is now the most stable one of the 3. and it's not close, because opening up two of those squares to become pentagons is a much greater relief of strain than opening up a triangle to a four-membered ring, which is what we saw with isomer 3,5. Now, what would happen if we keep going? Could I go 03, 04, 05? Yeah, sure we could, but I've, for the sake of time, I'm choosing to jump ahead. Let's move to the next slide here. What if we oxygenated these structures a lot? I'm going directly to N1206 here. And you can see all of the structures now have 6 oxygen atoms. Take a look at what's happened to isomer 3,5, the molecule on the left. The molecule on the left now appears to consist entirely of 6-membered rings. And, those of you familiar with organic chemistry, doesn't the molecule on the left now looks like it consists entirely of chair-conformed rings, chair-conformed 6-membered rings, similar to what you would find in cyclohexane, a very stable, classic molecule that we talk about with students in undergraduate organic. The triangles have been completely opened up. The structures are now completely relaxed, especially 3,5. But let's see what has happened. What has all of this additional oxygenation caused to happen to the relative energy? Let's go to the numbers. Oh, hello. Look what's happened. Isomer 3,5 with 6 oxygen atoms inserted into the structure, isomer 3,5 has now taken back over as the most stable structure. Now, why did that happen? Why did that happen? What you're seeing from N12 to N12O to N12O2 is basically a total relief of the ring strain in isomer 4,5, whereas isomer 3,5 still has strained elements to it. So the addition of the 3rd, 4th, 5th, 6th oxygen atom are really not relieving any pressure in isomer 4,5, because all of its pressure, all of its ring strain pressure, was relieved by the first two. What these additional oxygen atoms have done have opened the triangles of isomer 3,5 completely up, thereby relaxing that structure greatly and allowing it once again to become the global minimum. Okay? So, end of the day, what do we get from all that? Looking at a few conclusions here. N12 without oxygen favors the isomer 3,5 cage structure. Why? Because a lot of those atoms are surrounded totally by pentagons, which are idealized from an angular point of view, a structural point of view. As oxygen atoms are added, ring strain reduction occurs, but it occurs preferentially in the early going, at least. Ring strain relief occurs preferentially in the isomers that are bearing squares. The relief of the ring strain occurs more rapidly. A couple of reasons for that. A square becomes a pentagon in one move. The pentagon is an idealized structure for 3-coordinate nitrogen. You can oxygenate a square, it becomes a pentagon in one move. The ring strain's been relieved. And additionally, if you have a network of polygons where 2 squares are sharing an edge, insert an oxygen atom into the shared edge, and you're opening these squares up, relieving their ring strain. You're opening those squares up 2 at a time. So ring strain relief is going to occur very rapidly in the structures that are bearing squares initially. But with extensive oxygenation, the strain in the triangle bearing structure is completely relieved, and isomer 3,5, the triangle bearing structure, which was the global minimum before the oxygenation began, becomes the global minimum once again. Okay, so that's these are the discoveries that we've made. These are the data that we have, the conclusions that we've drawn. based on these computational studies. Again, remember, this is all computational work. We've not synthesized any of these molecules. So I'm going to go ahead and do my acknowledgments then. I just want to acknowledge just a lot of support that we've had over the years working on our research, grants from NSF and NIH, the American Chemical Society Petroleum Research Fund, and then also the College of Science, Technology, Engineering, and Mathematics. The CSTEM Dean's Office was very generous with our lab when it was time to upgrade to Gaussian 16. So we certainly need to thank them, thank the Dean's Office for that. That brings me to the end of the presentation. And what time we have for questions, I'll take it.
Okay, great. We have time for a couple of questions from the audience. Okay, you can either go ahead to ask your question or raise your hand. I do have one very quick. What are the experimental evidences? I mean, I'm an experimentalist, and how hard it is to make this kind of cage structure, and can you comment on their stability?
Oh, to stabilize, to stabilize experimentally.
That's right. I don't see. Remember, your top row is all zero, right? You started with a zero reference baseline when you compare.
Right. Well, I mean, any energy scale has to have a zero in it somewhere,
right.
Right. So yes, I'm talking about. You're right in that the data I was presenting represented relative stability, not absolute stability. I mean, you're right. It is very difficult to synthesize, but molecules and ions, such as N5, N7, positive ions, negative ions, molecules on that scale are known and have been characterized experimentally. Large cages like this with 12, 14, 18 atoms. I don't know that yes, those would be very difficult to do. Just to give some perspective on how energetic these molecules are. I went to a conference one time where a presenter was doing experimental work in this field. And what struck me was he showed a picture, the presenter showed a picture of an NMR sample tube, one end of which had been completely sheared off because his sample detonated while it was in the tube.
Wow.
So, I mean, yes, these molecules are very difficult to are difficult to stabilize in absolute terms in the experimental laboratory. I mean, that you're absolutely right. That's very difficult to do.
Yeah, thank you. Yeah, very, very interesting work. Any other question from the audience? Okay, well, with that, let's thank Dr. Strout one more time. Thank you, good job.
Okay.
And then with that, we'll close this session. I'd like to thank all the speakers and all the audience for participating. And I will turn the mic to Dr. Howie.
Okay, thank you for a great session. Thank you. And this is really the speaker from our our faculty levels. So we have a student talk and then finally move to the professor's talk. Thank you.